Welcome to endothermic and exothermic reactions. These are the two classifications of reactions in terms of what happens with energy. So in chemical reactions, we know that atoms get rearranged. But what happens in terms of energy? There's always going to be a change in potential energy. Whether potential energy increases or potential energy decreases determines whether we have an exothermic or an endothermic reaction. Something we need to understand before we can truly understand whether something's going to be endothermic or exothermic is that the more stable something is, the less energy it has. And that when bonds break, energy is absorbed. It requires energy. You have to add energy in order to break a bond. In contrast, when bonds are formed, energy is released. That is because the compound becomes more stable. So the more stable something is, the less energy it has. And the energy has to go somewhere, so it gets released. The first classification of a reaction based upon what happens with energy is an endothermic reaction. In an endothermic reaction, energy flows into the system. So overall energy is added to the system. I'll show you an example of one such reaction.
I brought some barium hydroxide octahydrate and some ammonium nitrate, and I'm going to combine them. So that must be the barium. Doesn't ammonium compound smell? They're both solids, okay? They're both white solids, powdery. There's the ammonium nitrate, there's the barium hydroxide, and I'm going to mix these two together. Hopefully I can get it all in there without spilling it. And put the top on because it generates something which stinks, and I'm just going to mix it around. It's an unusual reaction in that it's two solids reacting with one another. You don't see that very often because the point of contact between the two solids is very small. Two spheres touch each other at a point, whereas two gases can completely dissolve in one another, and so you get a lot more reaction going on. But in some cases, two solids will actually react with one another. So as this reaction proceeds, remember that we were releasing 2 moles of ammonia and 10 moles of water for every mole of barium hydroxide. Very endothermic. So I've got this little block of wood here with some water on it. I'm going to show you how endothermic it is by putting this, that's all mixed up. It's a nice slurry now because all that water's been released. And I'm going to stick it on that block, and I'll come back to that in a moment. I can show you just how endothermic this reaction really is. Oh, yeah, it is there. So that block is, it's so cold that it froze the water that I sprayed onto the block. And that's actually frozen right onto the thing. Not gonna let go. That's when it'll break off. Actually, it's there. Yeah, so there's a little chunk of ice. I don't know if you can see it from where you are, but there's some ice on the bottom of this thing. So it actually took it down to below zero. It's so endothermic, plus 80 kilojoules per mole.
So as you saw in the video demo, the endothermic reactions have a tendency to feel cold. The reason that they feel cold is because they take the energy from your body and it goes into the system of the reaction. So we're going to talk about what happens in terms of energy using something called a potential energy diagram. So we're going to draw a graph of the course of the reaction. So as the reaction proceeds, and we're going to have potential energy on the side, on the y-axis. So we know that energy flows into the system. So we're going to have reactants down here, and the reactants are going to start out low. As energy goes into the system, energy gets added and the products are able to form. So the products have more energy, more potential energy than the reactants do. So the course of the energy goes something like this. Now, in order to calculate the amount of energy that was absorbed by the system, we would take the difference between the products and the reactants. So we have the products here, the reactants here, And the difference between them is called the delta H of reaction, which is also the heat of reaction. And in the case of an endothermic reaction, we have a positive delta H. So it's a positive delta H, which means that if we have the reactants forming products, energy has to get added, so energy is then treated as a reactant. So we can write energy in on the reactant side. Energy plus the reactants forms the products. In contrast to an endothermic reaction, we have exothermic reactions. In an exothermic reaction, energy flows out of the system. Let me show you guys another example.
Up here is just a simple combustion. I have some methanol, which is a 1-carbon alcohol, and I'm going to spray some on the counter and just go ahead and light it on fire. And flames are given off, a sign that we have heat, and I'll give personal testimony. It's warm. We have yellow, orange, blue flames here. It's combusting. Heat's given off. That energy that's given off as heat came from chemical energy to begin with. Bonds are being broken, which costs energy, but then new bonds are being made and energy is being released. Let me go.
So as you can see, in an endothermic reaction, it feels hot. The reason it feels hot is because that energy is released from the system and goes into the surroundings. You're part of the surroundings, you can feel that heat. Again, if we draw a potential energy diagram, we have the reaction on the x-axis and the potential energy on the y-axis. Now, this time, instead of in an endothermic reaction, where the products had more energy, in an exothermic reaction, the reactants have more energy. So we're going to start off with the reactants up high, and energy is released to form the products. So it's going to go up a little bit and then go down to form the products. The delta H in this case is negative because, again, we take our final state, which is our products, and we subtract our reactants. So here we're going to have a negative delta H of reaction. Okay. And in contrast to the endothermic reaction, when we had the reaction that you saw in the demo, when reactants forming products, energy is released, so that is considered to be a product. So we would write energy on the product side of our reaction. Now, how do you actually calculate the delta H of reaction? We're going to use the equation delta H of products minus delta H of reactants equals the delta H of the reaction. So you have your constants page. On the back of your constants page, you have a bunch of tables, or you have one giant table. And on that table, it has a bunch of different substances and the delta H of formation for those. So what is delta H of formation? Well, delta H of formation is written like this. And what that means is it's the energy associated with the formation of a compound from its elements. So most delta H of formations, you notice, are negative because they're forming bonds from their elements, which makes, and when bonds form, we know that energy is released, so it makes sense that it would have a negative value with it. So to give an example of a delta H of formation, the delta H of formation is equal to the delta H of a reaction when it's the reaction that forms a compound from its elements. So for example, if we have H2 plus O2 forming H2O, and it's the formation of 1 mole of the compound, so we have to have a coefficient of 1 here. So that means we're going to have, we stick a 1/2 in front of the O2 to make that balanced. So in this case, the delta H of this reaction is equal to the delta H of formation for water. Now that's what the meaning of all those different numbers are. But how do we apply this to the delta H of reaction? Well, I'm going to show you guys by doing an example problem. So in the example, we have the reaction CH4 plus 2O2 goes to CO2 plus 2H2O. So we're going to use the formula delta H of reaction is equal to the delta H of the products minus the delta H of the reactants. So our products are CO2 and H2O. So we're going to take CO2 plus, and that's a gas, plus 2 H2O gas minus our reactants. So put parentheses to cluster our reactants together. So that's CH4 plus 2O2. Now we have to look up on the table that you have in front of you the different numbers that go along with these. So if we look up carbon dioxide gas, you should find that it's negative 393 kilojoules per mole. And then we add the water, but we need to multiply the value that's for the water by 2 because we have 2 of them in the reaction. So if you look up water, you will actually find that there are 2 values for water. You'll see one that has a little L here after the water, and you'll see one that has the G after it. We want the one that has the G because that means it's the gas. And it does differ, the amount of energy does differ, so the state is very important. So the water gas should be negative 241.8 kilojoules per mole. Then we're going to subtract the total of our reactants. So we look up CH4, and there's only one of those, which is why I didn't include the state of matter in it. And that is negative 74.9 kilojoules per mole. And then we also look up oxygen. We're going to multiply that by 2, and you'll notice that oxygen is 0. So we're just going to leave it at 0. When we crunch all of that together, and here's the thing, you have to remember to distribute this negative sign all the way through. In this case, it doesn't matter because we have 0 over here, but if we had something other than 0, it would matter. So you need to make sure that you do your order of operations appropriately, or that you remember to distribute the negative sign through all of the terms in the parentheses. When you should get negative 872 for your products, and that's kilojoules per mole. And when minusing a negative is like adding a positive, so we add the 74.9 kilojoules per mole, and we get an overall value of 802, negative 802.1 kilojoules per mole. So in doing this, you should find that because this is negative, that this is an exothermic reaction. So this is exothermic. And if I were to draw, or if I were, the next thing that the homework's going to ask you to do is to put this term back into the equation, put the energy term back into the equation. Because it's negative and it's exothermic, that means energy is released. And just like we saw before, the energy is then going to be treated as a product. So on the product side of our reaction, we then add 802.1 kilojoules. Now, the reason we do not, that this becomes positive is because this negative sign is just telling us to put it on the product side. It doesn't stay negative. It goes positive on whichever side you put it on in the reaction. So if this was a positive number, it would be positive over here. Because it's a negative though, it's positive over on the product side. The last thing that they could ask, that the homework will ask you to do, is to draw a potential energy diagram. So to do that, we know because it's an exothermal, potential energy is on the y-axis. We know because it's an exothermic reaction that our products have less energy. So we start off high with our reactants. And we're not going to write an R this time. We're actually going to write in what the reactants are. So we'll write CH4 plus O2. And then it's going to go whoop. And then our products are CO2 plus 2H2O. We also have to put our energy in here, and for our delta H value, so our delta H is equal to negative 802.1 kilojoules. Now, if you have any questions, please make sure that you ask them.